Hello everyone, welcome back to my channel. I'm Vishut Ramesh and today in this video I'm going to be talking about convolutional neural networks, its analysis, applications and prospects. So let's get started. So what is convolutional neural networks? So CNNs have become one of the most powerful models in deep learning, particularly excelling in fields such as computer vision, natural language processing and image classification. The paper provides as in-depth analysis of CNNs, highlighting their historical development, core architecture, and key innovations. CNN are renowned for their ability to automatically extract hierarchical features from raw data, significantly reducing the need for manual feature engineering. This survey also emphasizes the applications of one-dimensional, two-dimensional, and multidimensional convolutionals in various domains and suggests potential research directions for CNNs. So the history of CNNs. CNNs were inspired by the biological process of the visual cortex, where certain neurons respond to specific stimuli in an animal's visual field. The early development. The foundation was laid by McCulloch and Pitts in 1943, who created a mathematical model of neurons. In 1957, Rosenblatt introduced the perceptron, which was later developed into multi-layer networks. The introduction of propagation in 1986 by Hinton allowed for the training of deeper neural networks, overcoming earlier limitations. In 1998, Leaken et al. Developed LeNet5, the first CNN used for recognizing handwritten digits, establishing a baseline for modern CNN architectures. A breakthrough movement came in 2012 when AlexNet, a deep CNN, won the ImageNet competition, bringing CNN to the forefront of AI research and applications. So the overview of the CNN architecture. So it consists of the convolutional layer, which is the heart of the CNN. This layer applies a set of learnable filters to the input data, producing a set of feature maps that represent different aspects of the input. The pooling layer reduces the spatial dimensions of the feature maps while retaining important features, thus preventing overfitting and making the network more computationally efficient. Max pooling and average pooling are commonly used. Fully connected layer combines the features extracted by the convolutional layers to make final predictions. These layers resemble traditional artificial neural networks. Activation functions. CNN typically use ReLU, which is rectified linear unit, which introduces non-linearity, allowing the network to learn more complex functions. Other activations include leaky ReLU, PReLU, and ELU, which handle certain drawbacks of ReLU. Regularization techniques. CNNs employ techniques like dropout and batch normalization to improve generalization and avoid overfitting. So classic CNN models are, so first we're going to be discussing about LeNet5. LeNet5, proposed by Leaken in 1998, was designed for handwritten digit recognition and has 7 layers, including convolutional layers, pooling layers, and fully connected layers. It introduced key ideas such as local receptive fields, shared weights, and subsampling. LeNet5 pioneered the use of convolutional and pooling layers to achieve scale and shift invariance, making it foundational to modern CNNs. Though its performance was initially limited, LeNet5 paved the way for more complex and powerful CNN architectures. Classic CNN models. The next one is going to be about AlexNet. AlexNet introduced several key innovations such as ReLU activation, faster training due to reduced gradient saturation, dropout, used to prevent overfitting by randomly turning off neurons during training, GPU acceleration, used parallel computing to handle large datasets and deep networks, LRN, local response normalization, improved generalization by reducing activation noise, data augmentation, increase the training data through transformations like cropping and mirroring. AlexNet demonstrated the potential of CNNs for large-scale image classification, leading to widespread interest and rapid development in the field of deep learning. VGG-Nets. VGG-Net, proposed by Simayan and Zisserman in 2014, explored the effects of increasing depth on CNN performance, demonstrating that deeper networks perform better. VGG-Net uses 3x3 convolutional filters stacked in layers, unlike large filters used in AlexNet, making it computationally efficient and capable of capturing finer details. VGG-Nets comes in different versions such as VGG11, VGG16, and VGG19 with up to 19 layers. It proves that the depth of a CNN is critical for its performance, though deeper networks come with higher computational costs. VGG nets were highly influential in setting the stage for deeper CNN architectures and are still used as a benchmark in research. So GoogleNet and Inception networks. GoogleNet, developed by Kurdi et al. In 2014, introduced the Inception module, a breakthrough in efficient network design. Inception modules allow the network to choose the appropriate filter size for each feature, capturing information at multiple scales. GoogleNet has 22 layers but fewer parameters than VGGNet thanks to the use of 1:1 convolutions to reduce dimensionality. Later versions like Inception V2 and V3 introduced techniques like factorized convolutionals and batch normalization to further improve efficiency and performance. GoogleNet set the trend for creating deep yet efficient models, which was crucial for deploying CNNs on limited hardware like mobile devices. ResNet. ResNet, also called as residual network, introduced by He et al. In 2015, tackled the problem of vanishing gradients in deep neural networks using skip connections. These connections allow gradients to bypass certain layers, ensuring that the network can still learn effectively even it gets very deep. ResNet demonstrated that extremely deep networks outperform shallower networks in complex tasks like image recognition. Its ability to avoid gradient vanishing and degradation problems revolutionized CNN architecture, enabling the development of even deeper and more accurate models. So lightweight models, mobile nets and shuffle nets. MobileNet was designed for resource-constrained environments like mobile devices. It uses depth-wise separable convolutionals to reduce computation and memory requirements. MobileNet V2 introduced inverted residuals and linear bottlenecks, further optimizing performance for mobile and embedded devices. ShuffleNet introduced channel shuffling and group convolutions to maintain performance while drastically reducing computational complexity. Both models allow CNNs to be deployed on devices with limited processing power, such as smartphones, wearables, and IoT devices. So, the applications of CNNs: image recognition, achieving human level performance in object detection, classification, and image segmentation. Natural language processing, also called as NLP. CNN are used in text classification, sentiment analysis, and machine translation. Medical imaging. CNN is used for diagnosing diseases from X-rays, CT scans, and MRIs with high accuracy. Autonomous vehicles. CNN are crucial for recognizing objects, pedestrians, and other vehicles in real time. Gaming and entertainment. Used in visual effects, character recognition, and AI behavior modeling. Surveillance systems. Leveraging CNNs for real-time facial recognition and behavior analysis in security systems. So the challenges and future directions. So training CNN requires vast amounts of labeled data and convolutional resources. Overfitting remains a significant challenge, especially with small datasets. CNNs are often seen as black boxes, and understanding the decision-making process remains difficult. So future directions are development of more efficient architecture to reduce computational demands while maintaining performance. Increased focus on interpretable CNNs helping explain how networks arrive at decisions. Expanding CNN applications to new areas such as robotics, genomics, and other scientific fields. So the future environments could be deformable and dilated convolutions. These advanced techniques enhance the capacity of the CNNs to capture complex features and handle varying object scales. Attention mechanisms. Integrating attention mechanisms like squeeze and excitation networks improves model performance by focusing on important features. Continued architectural advancements. The exploration of novel architectures and training techniques will drive further improvements in performance and efficiency. Cross-domain applications. Expanding CNN applications into emerging fields such as robotics, autonomous systems, and environmental monitoring. So CNNs have fundamentally changed the landscape of deep learning and artificial intelligence, proving highly efficient in image and speech recognition tasks. The survey outlines the evolution of CNNs, highlighting their historical context, classic models, and innovations. While challenges remain, the future of CNNs appears promising, with ongoing research leading to more efficient, interpretable, and capable models across diverse applications. So thank you everyone for watching this video. I hope you now have a clear understanding about the CNN and its various models and its architectures. So please share, like, and also if you have any doubts, please put them down in the comment section below. Thank you.